Hello there. We are talking about energy and states of matter, and we're finishing this off with dealing with problems with latent and specific heat at the same time. So I'm going to give you some examples of latent and specific heat used at the same time. The only thing new about this is just being able to kind of sort it all and put it together, but the math is all review as far as what we've been doing in class the last few meetings. So what would be the energy change of 25 grams of steam at 150 degrees Celsius that cooled to 35 degrees Celsius water? Now, if we look at this, a lot of times people will make a mistake on a test and they will just use they'll say, okay, well, I've got steam and it's going to go from 150 to 35. So they'll use the specific heat of steam and do an energy and just do a temperature change from 150 degrees Celsius all the way down to 35 degrees Celsius. But that is not going to work because water at our normal atmospheric pressure is not going to be steam. I should say steam will condensate at 100 degrees Celsius. It won't. You don't have steam at 35 degrees Celsius. So we got to analyze what's going on here. What's happening here? So the first thing that's going to happen is as it loses energy, the 150, it'll lose energy. The sample will lose energy to 100 degrees Celsius. So the specific heat, this will be the specific heat of steam, will be used to calculate. That's what this lowercase c is, steam. This is our second workshop on this topic. If you need to go back to review how to calculate specific heat, that's what I'm talking about right here. This would be just like a practice problem from the second workshop, and it would just be using the specific heat of steam, and the energy change would be going from 150 degrees Celsius all the way down to 100 degrees Celsius. So this would just be like a practice problem that we've done before. But then once it gets to 100 degrees Celsius, it is not going to decrease in temperature anymore. As it loses energy, the molecules, it's losing kinetic energy, the gas molecules will start to come together as a liquid. And this is the heat of condensation. This is what we did in workshop 3, latent heat. So this would be the heat of condensation for the 25 grams. And this would be a phase change from a gas to a liquid, heat of condensation. And then once all that gas condensated to a liquid, if it kept losing energy, and it is, it's going to lose energy all the way to 35, now it's going to change temperature. But this is no longer steam, this is water. So this is going to be calculated with the specific heat of water. So part 1 that happened on this heating curve would be from our second workshop on this topic. The second stage would be the third workshop we did on this topic, and then the third one would be back to the second workshop. So specific heat calculation, specific heat of steam, latent heat, the heat of condensation, and then calculating with specific heat of water. So the total energy change here would be the energy from 1 plus 2 plus 3 would be the total energy change. So this is like using a lot of the workshops that we've been doing, but putting it all together in something more practical, more realistic kind of a situation. So let's work this problem out together. And if you think you know what you're doing, why don't you pause it now and go for it. And then when I work it out, see if we match. So let's work out the first step. The first step, it would be using a specific heat problem. And if you need a refresher on this, please go back and look at the second workshop we did with energy and states of matter, because this is really where I focused on specific heat here. The specific heat formula is energy equals Cm delta T. We know our specific heat. We look at it on our table. We have to look up those values, and you should have a handout. And if you don't, it's linked on the it should be linked on our webpage, but I'm going to pull it up for you if you're just using the video. So hold on one sec. I'll be right back. All right, I'm back. I found the handout. So I will have this. You'll be able to download this, but if you're just using the video, then you might need to go back to this slide or this point in the video to get some values off this slide here. So let's take a look here. So like I was saying, you'll get some values off there. We're going to talk about the specific heat of water. Specific heat of steam is what's going on here. So we're going to look at the specific heat of steam, which is 1,870 joules per kilogram Kelvin, and that's where I got that number here. So let's take a look here. That's where this number came from, your table. So you're going to need that table to pull up some information. So here's our equation. Here's our values. And just like we did in practice in workshop 2, you set this up. Make sure you set it up to cancel. Our specific heat times our mass times our change in temperature. Everything cancels out. We're in joules, and that would be the energy for the first situation. I put a little subscript 1, so the energy in the first stage is negative 2,337.5 joules. A lot of times students, when I do this in class, they'll say, should we answer those some proper significant figures? And you know what? I love that they're thinking. I love that they're starting to pay attention to the details and they're catching that. But one thing I want to tell you is we're not done. The question didn't want to know this stage. The question wants to know a whole bunch of stuff. We're adding all these stages together. And so we don't round off until we're all the way done. If you round off in the steps, you can make some big errors in the end. And this is something people embezzle money this way. They'll deal with large amounts of money for banks and stuff like that, and they'll just round off a penny here and there. In your account, what do you care? It's a penny. But when they're dealing with hundreds of thousands of millions of transactions, and they're still in a penny every once in a while, they're making a lot of money. So there's big errors, and people go to federal prison for that. I'm getting way off topic. But what I'm trying to say is we don't round off because your answer in the end will not be correct if you round off in the steps. So only round off when you're finally done. So we're not going to round off here. So I can see I have 2 significant figures in this problem. So, you know, I'm going to try to at least have 4 or more significant figures in my work. But if I can, I'll try not to round off at all. We shouldn't have different answers because someone rounded off in the work and someone didn't. Okay, the second step is the heat, the latent heat, or the heat of condensation. So this is a phase change. We're going from steam, we're going from a gas to a liquid. So this is a phase change here. And this is like our workshop 3. In workshop 3, we talked about these phase changes. And if you look back on that table I'll put it up again. Back on that table, we're talking about the heat of condensation of water. And the opposite of vaporization is condensation. So it should be a negative of this value right here. It should be the negative of that value. So that's what we got here, the negative of 2,259.2 joules per gram. That's the heat of condensation. And I'm just going to put our value of mass in here, 25 grams. The grams cancel out, and I'm going to get myself into joules. Like I said, I like latent heat calculations. I think they're pretty easy. And I multiply this together. You should run through this with your calculator along with me and make sure that you're agreeing with these values. Make sure that you're able to do it as I walk through with you on doing this. So negative 56,480 joules is what I got for the second stage. So to get to the second stage, it would be the first stage plus the second stage would get me to 100-degree water, because I'm at water right now because I phase changed, but it's still 100 degrees Celsius. You must write these heating curves. This helps you so much. If you don't do this, it's very difficult to figure out what to do next. And since we already did it, we knew what was next, and that was our third stage, and that is the specific heat of water will now cool from 100 degrees Celsius all the way down to 35 degrees Celsius. So I'm using the specific heat value of water. Again, look at your table for that constant. The mass, I had to convert it to kilograms because my constant's in kilograms. And my change in temperature is 35 minus 100. Remember, it's final minus initial, which is negative 65 Kelvin. I put these values together, and hopefully you've worked a little ahead and you did the same. And you can compare your answer with mine. Units cancel out. I'm left in joules. And my third energy change is negative 6,802.25 joules. Not done yet. I've just solved all 3, but the final question is, what is the sum of all 3? So the fourth thing we have to do is add up all the stages. So the total energy of this change would be the energy from part 1, part 2, and part 3 all summed together. So if I take those answers that we just solved and add them all up, I get 65,597.75 joules. Now I go back into my question. I see two significant figures here, two here, and 150 is two significant figures as well. Remember, this 0 doesn't count because there's no decimal place. Trailing zeros only count if there's a decimal place. So all of them have 2, but I'm always limited to my weakest measurement anyways. So I'm going to write this number with two significant figures. So that means I would just go to here. This 5 rounds this 5 up. So it's negative. I should put a negative here. My goodness, I forgot to put a negative. Let me do this right here, guys. I will fix this for my students, but we didn't see that in class. That's a negative. It's a very crooked negative. I did the same thing. I give up. All right, so negative 66,000 joules, or I might write it as negative 66 kilojoules. And that would be going back to our first topic and being able to use the metric system properly. Okay, that's our first practice problem. Let's try one more. This one I find is a little more difficult because what's being asked here is a 75-gram sample of ice has a temperature of 0 degrees Celsius. We're going to say it's two significant figures, maybe 0.0. I know the zeros don't count because there's no number in there, no other integer, but I'm telling you I want two significant figures. What state and temperature will the sample be after it is exposed to 35 kilojoules of energy? So what we're going to do here is analyze. I'm going to kind of do this repeating process of 3 steps. The first thing I want you to do is analyze what's happening. Well, adding energy to 0 degrees Celsius ice, would that increase the temperature of the ice, or would that cause a phase change? Would that change the temperature of the ice? Will it make the ice warmer than 0? Ice doesn't get warmer than 0 degrees Celsius at our atmospheric conditions. So adding energy to this point would cause a phase change. So the first thing you do is analyze what's happening so you know which formula to use. If it's a phase change, we're talking about latent heat. We're talking about the third workshop we did. So step 2 is use the calculation. We did step 1 to figure out what we're doing. Now in step 2, let's figure out since we know what we're doing, step 2 is to actually use the proper calculations. So we're going to use the heat of fusion because the ice is melting. The heat of fusion, we took a look at our constant. Again, you have to look at your handout at those constants. I don't want you to memorize constants. And then we're going to convert 75 grams into joules using our heat of fusion. And we cancel the joules out, our grams out. We're answering joules, and that's 25,020 joules of energy is needed to for the fusion of 75 grams of ice. The question says I've got 35 kilograms or kilojoules of energy. To do this, I used 25 joules, and this is actually 35,000 joules. So I only used 25,020 joules, but I have 35,000 joules, which leads us to our third step. Once we solve here, the third thing I want you to do is go back and look at the question and how much energy do you have and how much did you just spend. So return to step 1 if there is leftover energy. So step 3 is return to step 1 if there's leftover energy. So we had 35,000, we used 25,020 joules, we have 9,980 joules left over. Because there's energy left over, we go back to step 1. And then we reanalyze. And we keep doing this until our energy is gone. So we go back to step 1. What's happening? Just like we did before, but now we have to consider what just happened. This is no longer ice. We just spent 25,000 joules to turn the ice into water. So we're adding that leftover 9,000 joules to the 0 degrees Celsius water. Will that increase the temperature of the water, or will that cause a phase change to the water? Will that energy make that 0 degree water warmer, or will that energy turn that 0 degree water into a gas? And I think we know that water boils at 100 degrees Celsius, so it's not going to phase change. We're talking about a temperature change. And temperature changes are something that we did in our second workshop with energy and states of matter. And we talked about this, and we're going to be looking at the specific heat of water is 4,186 joules per kilogram Kelvin. We have this much energy left. This is what we ended with. Remember, this is the energy that we got from the last step. We've already used the heat of fusion. We used up some energy. So this number here is what we have left over. If you're curious, sometimes students, they're writing their notes and they're not really thinking, and then they'll start to come together and they'll say, like, where did this 9,000 come from? I don't see this in the problem. This is from what we just did, because this is no longer ice. This is water from heat of fusion. We use our formula, and I rearrange this formula here to solve for temperature. I'm going to try to use all of this energy and see what the new temperature would be, because that's kind of what the question's asking. So if we do this, we put our energy is our numerator. So the energy is what we have left. That's my numerator right here. And specific heat, C, is a denominator. So that's this value right here, my denominator, and it's joules, that's the joules right there, divided by kilogram Kelvin. So under here would be the kilogram Kelvin, but the denominator of my denominator, this is a denominator right here, and if there was a denominator under it, a kilogram Kelvin, that actually goes up to a numerator. So I put that kilogram Kelvin up here. That's from the specific heat right here. And I don't just keep putting fractions on top of each other. I put them on one line. And then over here I've got the mass, and it's 0.075 kilograms. Remember, this is in grams. I have to have it in kilograms to cancel out my constants. So we set this all up, and the answer will be in Kelvin. And it says that the temperature change will be 32 Kelvin. And this is actually a good thing, because we are heating up cold water, or 0 degrees Celsius water. If it heated up beyond 100, we would have to go and do another phase change because the water would be boiling. But it didn't, so we got to use up our energy and change the temperature by 32 Kelvin. And a change in 32 Kelvin is also a change in 32 Celsius. A change is the same. And if you're confused about that, go back, I think, to workshop 2. I talk about how change in Kelvin is the same as change in Celsius. So since the original temperature was 0 degrees Celsius, the change would increase to 32 degrees Celsius. Okay. Step 3, always go to the step 3. Don't forget this step, is return to step 1 if there's leftover energy. Well, is there leftover energy? No. We used all 9,980 joules. All of that was used. We used it right here. We used all of it to change the temperature to 32 degrees. So since it's all gone, we are finished. There's no more energy left over. The question is, what will be the state and temperature after it's exposed? So the state and temperature would be, it would be now water at 32 degrees. It would be right here. It would be water at 32 degrees Celsius. Okay. All right. So let's analyze what happened here. What just happened here was we had ice at 0 degrees Celsius. Energy was added to the ice, and the ice melted by heat of fusion, the latent heat. And then we kept adding energy to it, and it heated up that cold water now up to 32 degrees Celsius. And that used up all 35 kilojoules of energy. It ran out, and that's where we ended right here. So we ended as water at 32 degrees Celsius. Okay, so the final workshop is for this topic is as follows. These are kind of the culmination of everything we've been teaching and what you can expect for our upcoming exam that will be on this stuff. You should be able to handle questions like this. This really pulls everything that we've been talking about together in one question. So what would be the energy change of 83.2 grams of 29.4 degrees Celsius water changing into 217.0 degrees steam? So this would be like the first one we just did today. This question here would be like the second one we did today. The third one will be like the first one we did today. However, there's going to be a hint here. There's going to be 4 steps. We only did 3. There'll be 4 in this one. So give this a try. If you need help with this, let me know. That's what I'm here for. Good luck.